and it will be his first lecture on exploring random planar maps, slicing, peeling, and layering.
Okay, thank you very much. Thanks a lot to the organizers for the invitation to give this series of lectures. And yeah, so I'm going to talk about random maps and mostly metric aspects of random maps, and do a kind of survey of the techniques that are known to give actually quite precise results in the problem of scaling limits for random planar maps, in a particular, in a kind of a very particular class, which is the class of maps with a controlled either face or vertex degrees, which is at the same time both a very specific class and also a class that's oh sorry, yeah, I didn't turn it on. Okay. Yeah, which is both a very specific class and at the same time, a class that that is useful in many problems that that you wouldn't think of maybe in the first at first. So these maps in particular will be quite different from the ones that are considered, except in some particular cases, quite different from the ones that are considered by Jason in his lectures. So they are not going to be these mated CRT maps, which combinatorially are much more complicated, in fact, than the ones that I'm going to describe here. So let me start with introducing the model. So the model is that of Boltzmann planar maps. And okay, so if you are familiar with matrix integral, it's also known as the one matrix model. What you get when you consider integrals of a certain potential for one Hermitian matrix. So the setting is the following. So fix. Okay, so first of all, I don't have to define planar maps because Jason did that already, and we already had some talks involving planar maps. So I'm assuming that you all know what a planar map is, and but if there are any doubts, I will please don't hesitate to ask. Okay, so let us fix a weight sequence I'm going to call a Q, say Q1, Q2, Q3, and so on, which most of the time will be non-negative weights. Maybe in one or two proofs, I'm going to put them to to have them being formal variables, and then immediately after they will become again non-negative weights. And we consider an associated measure I'm going to call a W index Q on the set of bipartite rooted plane maps. And so in this case, so rooted plane map means that it's a map embedded in the plane. I'm not considering surfaces of higher genera. Rooted means that one of the edges has been distinguished and given a particular orientation. Okay? And so when you have a root edge, of course, you have a root vertex, you have a root edge, and you also have a root face, which is, say, the face that sits to the right of the oriented edge. And in this setting, bipartite just means that all face degrees are even. Okay, so it's a gluing of quadrangles, hexagons, and so on, but I'm not allowing triangles and so on. So, of course, this is a kind of a strong restriction, but it makes the combinatorics much easier. even though most of the results that I will describe, should be essentially the same in the non-bipartite case, say up to technical complications. Okay, and so we now define this measure WQ of M to be the product over all faces of M of Q indexed by the degree of the face divided by 2. Okay, so again, M rooted bipartite plane map. Okay, and actually I'm going to modify a little bit this definition by saying that F is different from the root face. Okay, so I'm not counting the root face, say, as part of the map. I want to sort of consider that as an exterior face. Okay. Now let us define the total mass of this measure, WL of Q. So this is going to be WQ of the set ML, where ML is the set of bipartite plane rooted maps with root face of degree 2L. Okay, so this, maybe you want to consider that as the set of maps with a boundary. So here, for instance, at 1, 2, 3, 4, 5, 6, 7, 8. And so this, for instance, I don't know. So this map is an element of M4. And I should stress at this point that, in fact, nothing tells me that the boundary should be simple or anything like that. For instance, there could be at the same time, multiple edges in the map. There could be edges that, whose both sides lie in the same face, and also the root face. So I didn't actually write the root. Also, the root face does not have to be simple. So for instance, this is an element of M5. Okay, it really the exterior perimeter is really equal to 10. I mean, yeah. Okay. Any questions about that? So note in particular that this W1 of Q, well, this is, let's say, the partition function. If I want to think about this model as being a kind of model of statistical physics in which the configuration is a map. So I want to call the total mass of this measure the partition function. And this would be the partition function for all bipartite rooted maps. And why is that? It's because I can always see, so this is the total mass of bipartite maps with an exterior face, root face of degree 2 times 1, okay, so 2. And the reason is that if I have such a map, so let's say something like this, okay, then I can always close or open in this direction let's say the root edge or face. So meaning that I can always take this 2 gon and shrink it to a single edge. Okay, so doing an operation of this kind. Okay, and of course it is a bijection. Okay, so let me give a couple of examples why these measures are interesting. So let me start with a kind of trivial example. which is when Q is equal to Z times delta of P for some non-negative Z and sub P greater than or equal to 2. So in this case, so all the weights are 0 except the one with index P, and that means that all these weights are going to be 0 except for maps in which all the faces different from the root face have degree P. Okay? So in this case, WQ is the counting measure on the set of what I want to call 2P angulation with a boundary. So by with a boundary I mean root face of arbitrary even degree. And of course, because of this Z that counts for every face of the map, I want to weigh this counting measure by Z to the number of faces of the map M. Okay. So if I want to study a uniform 2P angulation with a fixed number of faces, I just have to condition this measure on this particular subset. So this is one kind of trivial example. And okay, so of course, if you take, for instance, a weight sequence Q to have a finite support, then you will just obtain maps. Let's say that Q1, Q2, Q3 are non-zero. Then you will obtain maps that are gluing of two gones, quadrangles, and hexagons, and the frequency of appearance of all these faces will depend on the particular choice of the weights that you had. Okay, and in fact, this context with a Q of finite support is the context in which most of the studies in the one matrix models have concentrated on. It's the situation where you take a potential which is a polynomial in the matrix, but here we really want to consider this general setting and consider weights Q that have an infinite support, because it's actually something that allows you to obtain very different phenomena than just the situation with, let's say, uniform quadrangulations or 2P angulations. Okay? So this second example gives a motivation for that, and it's the rigid loop ON model, which was introduced by Borot, Boutier, and Guiter in around starting of the, okay, it's a little bit strange to write it in that way, but around 2010. And so it goes as follows. You consider a map with two types of faces. So first of all, you have, just as before, faces of arbitrary degree 2k that are weighted by the same sequence qk as before. And you also allow a second kind of face, which are quadrangular faces that are traversed by a little piece of loop. Okay, so let's say that's a piece of loop. So what it means is that the map that you obtain, I mean the maps that are allowed in your class are maps that are obtained by gluing these two building blocks, but of course in such a way that a piece of loop connects with another piece of loop and forms closed red loops. Okay, and this you give it a weight, let's say h, and you are going to weigh every loop. So again, a loop is really something that is obtained by a gluing of such quadrangles. So I'm not drawing it all the way, but you should imagine it in this way. Every loop gets a weight little n,
where n is not an integer. N is some real number. Okay, let's say some positive, non-negative real number, and h as well. Okay, so consider this associates. I mean, you can consider a natural measure WQHN, a measure on such a loop, or say. So why is it called rigid? It's just because the loops are only allowed to traverse a quadrangular face in this way. It can only go from one side to the opposite side. Okay, it cannot turn. Hence the term rigid. So on such loop configurations, and let's say that WQHN of a map M. Okay, so M again is really a map that is formed by these two particular kinds of faces. It's going to be the product over normal faces, let's say normal of Q degree of F divided by 2, H to the number of pieces of loops, and N to the number of loops. So this defines a decorated model of maps. They are not really random. For now, I just have a measure, but if this measure is finite, I can just divide by the partition function and obtain a probability measure. So if something tells me when this measure is finite, then I can define a natural probability model on this loop configuration space. Okay, and so this is not at all a model of this kind. It's more complicated, but you still can say something by doing the following thing. So typically, a loop configuration will be something again with some normal faces that are not traversed by loops, and then you have loops that, of course, can be nested in a kind of arbitrary way. And then what you can do is you sort of empty the interior of the loops. Okay, so let's imagine that the root face sits somewhere here. You can just, okay, let's remember that these loops are really trapped between this kind of rail track here, and we just emptied the interior of these rail tracks. Okay, and by this we mean that we really dispose of everything that's sitting inside. So if we do that, we obtain an operation that is, let's call it phi maybe. It's called taking the gasket of the map, and we obtain now a map with a certain number of faces that can be of two types somehow. The faces that were sitting here, sitting in the map in the beginning, and these newly created faces. And my claim is that if you pick a map according to this distribution, say, and you push it forward using the gasket decomposition, then you obtain a map which is one of these maps. And so by this I mean that phi of WQHN is equal to WQ tilde, where Q tilde of K is equal to QK, meaning that every face in this new map could come from a face of the original map and count with a weight QK, or it could come from one of these loops. And how does it count? Well, it counts with a weight which is equal to n, because I've counted one loop. Okay, h to the power, which is the perimeter of this loop, which is 2k because I have a face of degree k, and I have to multiply by WQNH, the partition function of all maps. So let me put a tilde here to mean really loop configurations with perimeter 2k. Okay. Yeah.
Is my understanding correct that this rigid loop model was the same as
some version of the ON model on the map where the loops are not necessarily disjoint, but they can't cross. Is that correct?
So
With that constraint, you can use I mean, you could have, say, 2 layers of loops that are just correspond to the same.
So I'm not sure. They cannot cross, of course, because But
when you sort of collapse your loop.
Yeah, I see what you mean. So
loops, then you get an ON model on the thing with the collapse. I mean, it's just a way to.
I think so I think what would be called really an ON model would be the situation where you take only, let's say, triangles in both cases, and you allow the triangles to be crossed from one side to the other, or you consider quadrangles that can be crossed by 2 loops in this way, something like that. But this is a simplification. It's you just do not allow this.
No, but I mean, the loops are living on the edges, not on the face.
Right. Okay. So sorry. So they are living on the dual graph. Yeah. The loops are living on the dual graph. If you.
So those ones, yes, but you can represent them as. Okay. It's just a way to say that actually they live on the same graph. Is that my understanding correct? The rectangle, you can identify the rectangle with the edge.
Yeah. Okay.
Okay. So that's just sorry.
Yeah. Okay. I mean, besides that, is the model clear? I mean, maybe. Okay. Okay. So these are really the motivating examples, and you see that in the second example, clearly the weight sequence Q will not be of bounded support. Okay, now let me concentrate on what I'm going to call admissibility. So let us say, or let us call that Q is admissible if WL of Q is finite for some. And it's not difficult to see, hence every L greater than or equal to 1. Okay, so I'm just saying that Q is admissible if the model here gives rise to a well-defined probability distribution. For instance, if I divide WQ, restrict it to ML and divide it by WL of Q, I obtain a well-defined probability measure on ML. Okay, and in this situation, I say that Q is admissible. Okay. And of course, the first question that you can ask is when is Q admissible? And actually, this question also makes sense in this slightly more general setting. And we see that if we know when Q is admissible, maybe we'll be in good shape also to answer this question here. Okay. And let me give the following proposition. So let GQ of X be the generating series of QK, except that I'm going to put a little tilde. So Q tilde of K is just going to be a small binomial factor 2k minus 1 choose k in front of qk, and then q is admissible. So I don't know if you can see here actually. Can everybody see? I mean, we push this, but yeah. So q is admissible if and only if. Okay. GQ of x equals x has a solution x, let's say, greater than 1. And in fact, the solution can be only bigger than 1 because actually I didn't define q tilde of 0, but let me fix that to 1 by convention. Okay, so G is bigger than 1. Sorry, Bertrand. Yeah. GQ of x equals x. Okay. As a solution. So it's a very, very simple criterion, and I'm going to explain why it holds. And on the way, it will give us some interesting ways to understand these maps. Okay. So in fact, I should mention that something slightly stronger than that is true. So let me make a remark. In fact, Q is admissible if and only if W, let's say 1 dot Q is finite, where this, by definition, is equal to the sum, okay, the sum over all maps, so that would be in M1, of WQ of M, so far it's just the definition, but I want to multiply by the number of vertices of M. So if you like, this is the partition function for a slightly different model of pointed maps, in which, so if you like, this is the partition function for rooted and pointed maps. Okay, so by rooted and pointed, I mean that I have, again, my root face somewhere, but I also have a distinguished vertex V star sitting somewhere in the map. Okay, and of course, if I take the sum over all possible vertices, I will obtain this factor here. So this is a strictly, I mean, it seems like a strictly stronger condition, but in fact is not. As soon as this series is finite here, then this one is also finite. Okay, and today I'm going to use this fact. I'm not going to prove it. I'll try to do it next time if I have time. But I'll use this stronger notion of admissibility for now. Okay. So in this lecture, we admit this fact. But I think it's a little slightly surprising fact. It holds in this level of generality. And so the second remark is that so if Q is admissible, so if GQ of X is equal to X has a solution, well, it cannot have many solutions because G is obviously a completely monotone, so in particular a convex function starting at 1. So it can have at most 2 solutions. Okay? And in particular, it means that there is a smaller solution. Okay, then, okay, there are at most 2 such solutions. And it turns out that RQ, which is the smallest solution, if there are more than 1, is given by 1 plus W1 dot of Q divided by 2. Okay, so it's again a remarkable fact that you form the generating series of the Q case. Maybe you have this extra factor that comes from somewhere. I don't really know. You solve this very simple fixed point equation, and it gives you something about the model. So so it turns out that this 1 plus W1 of Q over 2 counts something. And I want to interpret this as the generating function, or the partition function, for objects that are called slices. And so the terminology of slice was introduced by Boutier and Guiter. It also appears in the work by Le Gall under different name of maps with geodesic boundaries. And I want to explain what a slice is. So I guess that about half or 3/4 of the audience have seen before the bijections by Schaeffer, Boutier, Di Francesco, Gitter, and so on. But in fact, it turns out that these bijections have a nice interpretation of in terms of these slices, and I want to try to describe that for you today. At least it makes these bijections a little less magical than it might seem at first. Okay, so what is a slice? So again, I have a map which is rooted and pointed. And this is what is described by a W1 of Q over 2. So I'm going to get one extra map by allowing just this map. And so it's going to count somehow as the root and the distinguished vertex here. You see, this map, somehow if I count it according to the measure WQ, it's not there because the root face does not count, if you like, in the map that I'm counting. And this one has no face besides the exterior face. Okay, so somehow I want this to be singularized as an element with weight 1. And now I have all the maps which have at least one, let's say, non-root face, so non-trivial maps, if you like, which are both rooted and pointed. But they are also bipartite, meaning that there are only two situations, which is that the root either points to or away from V star. In the sense that if I look at the graph distances, let's say L prime, so let's call L the graph distance to V star of, okay, so let me call E this oriented edge of E minus and L prime to be the graph distance to V star and of E plus, then necessarily L minus L prime has to be equal to 1. Okay, the graph distances have to differ by 1 because if it were not the case, then I could construct, by taking two geodesics to the ends of this edge, I could construct a cycle with odd cardinality, odd length, and that cannot happen because the map is bipartite. Okay, so in particular, L prime has to be L minus 1 or L plus 1, and it gives me a partition of the set of all these maps into 2. So by dividing by 2 here, I'm going to say that I'm keeping only those for which the root edge points towards V star. Okay, so this counts. Okay, so I call that slice, and now I have a first definition. So rooted pointed maps with the root pointing to V star. Yes, so maybe this is the first definition. So when I have such a map, I can, in fact, consider one of these shortest paths to V star, starting with the root edge. Okay, so I can just take the first step of my path to be this root edge. I know that it belongs to some shortest path or geodesic path to V star because the distance is decreasing when I travel along this edge. So what I can do is, so here I encounter another vertex. I can try to take the vertex that is at most to the left as possible, but still on a geodesic to V star. Okay, so maybe it's this vertex and then that vertex and so on. So here, this red path is going to be a leftmost geodesic to V star, starting with the root edge. Okay. So that makes sense, and it's uniquely defined. But then what happens is that I can cut open, I can use this geodesic path to cut open the map in, I just take, if you like, a pair of scissors, and cut along this red path. So you should imagine that this is a sphere of paper or of a soft material. I cut it open using a pair of scissors, and it's going to duplicate for me the red path. Okay, so I'm not good at drawing scissors, but you should imagine that you cut open. And of course, this operation is invertible. You can, if you have cut and you keep the position of the root somewhere, then you will be able to rebuild the map that you started from, at least if you have some glue with you. Okay. So what you obtain, so by cutting open along the leftmost geodesic path from the root to V star, you get a map with two boundaries. Okay, so here was the initial root of the map, and here was the distinguished vertex V star. And this red and of course this is all discrete here, right? So this red and green path are two geodesic paths of equal length. But okay, so I should say that the map is sitting inside here. Okay, so maybe let me try to be more specific about that. If I take a little bit of the map here, this grayish part here, then this part is going to be here on this picture. So the map sits inside, and what's sitting outside of this map is what was in the rift that I cut open. Okay. So it's maybe it's a little hard to see, but that's also the reason why the green part that was sitting on the left now sits on the right. Okay, maybe you have to think a little bit about that. Okay, so you have two geodesic paths of equal length from this base vertex to the top vertex, and moreover, since the red path in the initial map was the leftmost geodesic path, there is this extra property that if you take any path that starts from the green part and returns to it, then this cannot be a geodesic. Okay, because otherwise it means that I could have shortcut, well, the red path sitting up here by this path. So it cannot be a geodesic. Okay, and this is my second definition of slice. Okay, so slice definition 2 is a map with boundary having these two properties. So namely, this is property star, and this is property double star. And it's in a perfect bijection with the map that I've considered above here. Okay, so what I want to explain in the remaining time is why this is useful, and in particular why it can give this statement about admissibility. And for that, so I mean, in many talks on random maps using bijections, at some point you have a bijection with trees, and in fact I'm not going to describe it. In the end, we'll use it. But I'm going to try to explain to you where it comes from, this model of slices. Okay, so maybe this is 3. Yeah. So the slice decomposition So this decomposition is due to Boutier and Guiter, and it starts with a rooted pointed map, let's say with a perimeter, with boundary of perimeter 2L. Okay, so I have maybe something like that. So again, there is no reason why the boundary should be simple in principle, but it's easier to draw pictures with that. And so sitting inside the map, I have a vertex V star. Now let us look at the vertices of the boundary. And again, because of this bipartite nature of the map, if I record the distances to V star, then these distances are going to move always by +1 or -1 if I move along the boundary. Okay? So if, say, this L, so L is going to be the, let me call that V. So L of V is the graph distance to V star. Then this guy can either be L + 1 or L - 1. So let's say L - 1 maybe. This one will be at distance maybe L - 2, L - 1, L, L - 1, L, L + 1, L, something like that. This is one of the possibilities. Yeah, sorry about that. Say 2K. Okay, so in particular, if you have this pointed map, then you have a first kind of data that you can record, which is the set of these label increments along the boundary, or the set of labels along the boundary. So maybe let's start from V. Let's imagine that the root edge is here, and so you get a discrete bridge of length 2K this time, starting and ending at the same point, which in this case is L. So you have L, then L - 1, L - 2, L - 1, L, L - 1, L, L + 1, and L. And you finish at 2K. Okay, so this just records, again, the graph distances to V star. Now what you can do is you can again cut open this map with a boundary by taking these leftmost geodesics. So I have to do it in a slightly careful way here. Yeah. So let me take all the edges which are decreasing. Okay, so I'm going to mark them with a little star. So it turns out that the root edge is in this of this kind. I have this one and I have this one. Okay. Then what I'm going to do is so in particular, so these are not root edge, but they go in this way. If you want to go to V star. Okay, so you travel in this way. Here you travel in that way. Here in that way. L - 1, L - 1. In that way. So I just oriented the edges in such a way that they point to V star. And now what I do is from these vertices here, I draw the leftmost geodesic going from this edge to V star. So I obtain a path like this. Then I guess from this point I also have the leftmost geodesic traveling to V star. So maybe something like that. And from this point, I'll also have, let's see. So I guess I'm done in this way. So okay, in order to do something a little more interesting, I should say that these paths do not have to meet necessarily at V star. Okay, in principle, they could meet before arriving at V star. And I do, if you want, I cut open along these geodesics again. Let's see, so I have this L, L - 1 in this way. And again, I end up with a collection of slices. So in this particular example, I've not been extremely careful because what I want to do is that, okay, so this example was really badly chosen. What I want to do is, for these edges, I really want to consider that this is a trivial slice, if you like. Okay, yeah. So the bigger picture that I want to draw is if you start from a descending edge like this, LL minus 1, then you want to start this green path and go inside the map to V star, and let's say that this is L, and you will have another slice on this side. So maybe this is L plus 1, and then L, and then you have another slice like this, and so on. So my point is that if you have two consecutive edges like L minus 1 and L minus 2, then you want really the slice to be associated with this one to sort of overcome the slice that starts from this guy. Okay, so the slice associated to this edge will just be the trivial slice made of one edge. It's completely swallowed, if you like, by the slice that started from this vertex. Okay, so okay, so in this example, it was not extremely clear. Yeah.
From the left two vertices.
Sorry.
I mean, you can still have red paths from the left two vertices, right?
Which one?
The one and the one above.
This
left.
one.
The L and the L minus 1, yeah, to the left. You could still have leftmost geodesic.
No, because I mean, yeah, but I want to consider. Okay, so. No, but that's not the way I want to do it. It wants to start a red path, but it's trapped by this green slice. Yeah. So yeah, I want really to have this convention here. Yeah. Okay. So sorry for this non extremely convincing demonstration, but sorry, let me think about that. No, I'm sorry about that. You're right, of course. Yeah. You're right. Yeah. So there is a red principle. There is a red path that starts from here, okay, and there is one that starts from there, and the slices. Yeah. Sorry, I got confused. And the slices are defined in this way. And of course, you're right. Yeah. So okay, let me try it again. From every vertex, you start a leftmost geodesic path in red in this way. So you obtain this set of coalescing paths going to V star that are in red, and you color in green the edges that go from let's say L to L minus 1, going in counterclockwise order along the boundary. And you cut open the red path. Yeah. So in the end, what you obtain is a bijection between these maps, which are rooted and pointed maps with perimeter 2K, and pairs that are made of a bridge of length L. And for every downward step of the bridge, so the one that were marked with these little stars here, you have one slice. Okay, so you get one slice for each descending step of the bridge. Okay, And one way to think about it is that you can imagine the slice as sitting, has been hung, if you like, under the graph of the function on the top of the descending path. Okay, so here you have maybe another slice, and there you have another one, and there you have another one. So again, these are all slices with the definition that I gave earlier. And the bijection, so in this way, this is the way it works the way I described it. And in the other direction, what you do, so in this direction, what you do is you glue the slices horizontally by connecting the green parts to the red parts that are facing them. Okay, so for instance, this one, let me use another color, maybe this one is going to be glued to that part, and so on. And of course, you connect the parts that are facing each other, but that are not blocked by the bridge here. Okay, and this gives actually a bijection. Okay, and in fact, this bijection it results in a branching structure for the slices. Why is that? Well, if you consider, so let me still use my kind of a color code here. If you have a slice, so which is routed downstairs here, then you can explore it by revealing the face that sits on the other side than this geodesic. Okay, so it's going to be some face with okay, 1, 2, 3, 4, 5, 6. Okay, with even degree, and then what you can do. So again, all the geodesic paths are aiming for this star, and what you can do is you can consider that this is now the exterior face, and you can perform a slice decomposition in the same way as I've done above. Okay, so for instance here you will get, I don't know, so you will get some label L, maybe here L minus 1, L minus 1, L minus 2, and this has to be L minus 1. Okay. Again, you look at, so this time I want to be a little extra careful here. So you want to look at the edges that point in this direction, and you mark them with a star. So this is a star here, and this is also a star. And then you perform the slice decomposition starting from this guy. So maybe you have L minus 1 here, and that's it. And what you see immediately, is that given the degree of the face that you have uncovered here, you have a decomposition of your initial slice into a number of sub-slices, and then you can continue. Okay, and so the way in which the Boutier-Di Francesco guitar bijection works is just taking the vertices that are at the bottom of the slices in this way. Okay, there's actually one too much. Let's see. That's LL minus 1. It should be this one, but for some reason I don't want it. So okay, so sorry, so I got confused. So okay, I have one too many. So sorry about that. But the idea is that you connect the bottom vertex to a black vertex. This vertex is going to be connected to the bottom vertices of each of the slices, and then you can continue it this way. Okay. So again, sorry for this. It was it's not very well done. So what you get in the end is this gives. So okay, decomposing at the root face. Okay, the face on the other side of the root edge recursively results in a tree decomposition of the slice. And how does it go? So this tree has two types of vertices. So you have, let's say, the white vertices and the black vertices. And these types, I mean, these types of vertices alternate, okay, between generations. And what happens is that the degrees of black vertices, they correspond to the half degrees of the faces. Okay, so I'll have one black vertex for every face of the map, and its degree will correspond to the half degree of the corresponding faces. And that's actually a bijection between slices and what are called the labeled mobiles. So I'm realizing that I didn't define what are the labels. And the labels, they are just given by the graph distances to V star. Okay, and if you look at this, you see that the rules for these labels. So labels are just the graph distances to V star, and may be shifted by the root label. So it's good to have the convention that the root in fact gets the label 0. And if you look at the condition that this labeling has to satisfy, you obtain the classical condition that if this is L and this is L prime, then L prime minus L has to be greater than or equal to -1. And of course, L prime are integers. Okay. Okay, so yeah, so sorry for this poor presentation at the end. So I'm realizing that I'm already over time. So tomorrow I will give. Okay, I will recall the basic of these bijections to give a proof of this admissibility criterion, and then I will show how you can use this coding by trees in order to get our first scaling limit results for maps. And then the plan is that after this, so at the end of probably the half of the next lecture, I will move to another exploration of maps, which is in fact even more classical, which is the peeling exploration of maps. And this in turn will tell us something, not about the distances in the map, but the distances in the dual map. So it's actually a kind of funny thing with these Boltzmann planar maps, that they are actually connected at the same time to both of these very classical objects and fundamental objects of probability theory. First of all, random trees, which is the one I'm starting with. But in the case of peeling, they are also connected to the classical theory of random walks. And and this is what I will spend, I think, most of the last part of the lectures to discuss. And in the end, if I have time, I will discuss the third description of maps, which is called the layering, in order to try to connect the properties of distances to the properties of dual distances. Okay, I'm done for today. Thank you.
Questions? And a small question. On the board there on the right, you said it's equivalent to have this W L of Q finite for some or every L.
Yes.
Is that obvious?
It's not difficult to see. I mean, you just essentially you decompose. If you like, you decompose according to the root vertex, and I mean not the root vertex, but to the root face. I mean, it's a very simple thing to see. Yeah.
Other questions? Okay, if not, so we have the coffee break, and we start again at 11:15.